So welcome everybody to our STEM series, our forensic science STEM series with Mr. Michael Haag. And I hope I pronounced your name right, by the way. But thank you all for joining us. Before he gets started, there's just a couple of housekeeping announcements. One is, please feel free, if you guys do have any questions, to please type them in the chat. If you're not sure what the chat is, it's the little bubble at the bottom and it works like a text message. If it's appropriate and the time allows and you're able to on your computer, please also feel free to chime in with your microphone and ask a question. Otherwise, just enjoy. At the end of the session, I will put a link into the chat box, which is the attendance verification link. So make sure before you leave the session that you make sure to fill that out so you get credit for attending today. And I'll put that in about 5 minutes before the end of our session. So with that, I will go ahead and turn it over, and I will, just to save on broadband space, I am going to go ahead and turn my camera off, but go ahead and get started.
Sounds good. Thanks guys for being here. This will be a new experience for me. The Zoom environment is certainly one we're all trying to get used to, but I'm going to tell you kind of how I've organized this presentation. This is a general forensic science presentation. So it's going to cover multiple areas within the crime lab. I think you'll quickly see that unlike TV, if any of you are fans of things like CSI and NCIS, that no one person does everything. Same person that analyzes firearms probably isn't going to be doing DNA, isn't going to be out there, putting handcuffs on somebody. So that's what I'm going to kind of break down into categories to start off. It's each of those disciplines within the crime laboratory itself. But when I do these lectures, whether it's in person or like this, one of the critical things that I'd like to ask of you guys is that you ask questions as we go along, whether it's via the chat. I'm going to try and keep an eye on that. And if anybody else sees that there are some chats coming up that I haven't seen, please just holler out and flag me down, or turn on your microphone. Yeah, Ling's got it covered. Or turn on your microphone and just holler at me, because I'd very much prefer to take those tangents as we go along instead of trying to remember them to the end and then not knowing where we were. Sometimes those questions are some of the best questions that we get, or that I get, and the most entertaining on my end. So please do that. And then besides my sort of organized presentation, at the very end, I really want to have quite a bit of time for question and answer, because again, that's where I think that you guys get the most out of this, instead of just seeing some canned presentation as we go along. So that having been said, I'm going to start off and get my screen shared here. And hopefully we've got the main slide up. Ling, can you give me a thumbs up if that's going well? Perfect. All right. So first, a little bit about structure. Like I was saying, no one person does everything. And there are so many disciplines, and it requires so much training and education in each one of these disciplines that we specialize very highly. So this is how my crime laboratory is structured. Not every crime laboratory will be exactly like this, but it's pretty common to be along these lines. So what I'd like to draw your attention to is the box starting with the crime lab director and the one above it with crime scene. Now, there can be some significant overlap between the people in the laboratory and the people at a crime scene. It just depends on where you are in the country and how your organization is structured. For today, we're going to focus primarily on crime laboratory. However, especially with my specific discipline, firearms, there is a lot of crossover between what we can do in the laboratory and what we can do in the field. Within a crime laboratory, then you have multiple forensic disciplines. So with mine, the head of the physical identification unit is me. So I have 3 different units under me. I've got controlled substances, the blood alcohol unit, the breath alcohol unit, and the firearm and tool mark unit. So you'll see that I may be able to answer some of your questions in those areas a little bit more deeply than some of the others, like the latent fingerprint unit and the DNA unit, which are the other primary ones that we have here in Albuquerque. Now, other laboratories may have units such as a trace evidence unit. That's a unit that would look a lot at hairs and fibers, maybe paint samples, things along those lines. But those are pretty much going to be the biggest units you're going to find in most crime laboratories. Things like bite marks, that might be a topic for discussion at the end. That's not done nearly as often as it was, nor is, say, handwriting, as an example. And if you're thinking that psychology or forensic psychology is typically a part of a crime laboratory, Unfortunately, it's not. That's often in a completely different unit. So the units that I'm talking about here that my system focuses on are the physical evidence units. If it's something tangible that you can collect from a crime scene, that's what we're going to work on a lot in this section. So first, we're going to talk about controlled substances of those about 4 or 5 different sections. So of course, controlled substances are important because in many cases, if someone is taken into custody under suspicion of possessing a controlled substance, you need to have some sort of actual test behind it to make sure that it is indeed, say, cocaine, as opposed to baking soda or oregano versus marijuana. So we have a system, we have a process, and what you'll find that is consistent between the vast majority of the systems or the disciplines that I'm going to talk about today is that there's always a comparison of a known to an unknown. It's not like TV, for example, with DNA, where you can take a DNA swab from someone, plug it into some magic computer somewhere, and all of a sudden it pops up with an indication of who the person is, what they look like, and where they currently are residing. Not like that at all. Unless you have a known specimen to compare to, whether it's drugs, firearms, or DNA, the forensic scientists can't really come to their full potential. So with drugs, for example, my laboratory possesses all the licensing to possess all these controlled substances. So we have everything from fentanyl to heroin to cocaine of 2 different main types to all of the synthetic cannabinoids you might have heard about over the past few years, because we use these as our known standards. It's our library, if you will. So once you understand that basic fundamental property of all the forensic disciplines, let me walk you through how we do some of our controlled substances analysis. First off, we're going to start with a visual examination. Some things can look similar. For example, powdered fentanyl versus cocaine. Without an actual test, and certainly you wouldn't want to touch the fentanyl for reasons we'll come back to in a minute, but without an actual test, these things could look very similar to something that isn't controlled, like baking soda or a million other things. So a visual is huge. We're going to determine whether we're looking at a typical white powder, or whether we're looking at a plant material, which is potentially going to be marijuana, or whether we're looking at something that's, say, tarry in consistency, which might lead us down the road of heroin. And depending on that visual examination, it's going to determine significantly where we go from there, what set of processes we're going to do. So for example, if it's plant material, a microscopic examination is going to be big for reasons I'll show you in pictures in just a second. Whereas if it's a white powder, we may go to color tests. And that will help us figure out what family of potential controlled substance we're dealing with. And then in the end, what I'm going to come back to and wrap up with is actually GCMS, which is gas chromatography or mass spectrometry. This is the heavy hitter. This is in controlled substances, our big final end tool that is sort of the end all be all. So let's walk through this a little bit. First, a visual examination. Here you're looking at 2 different kinds of potential illicit substances. The colored pills in the back are what we've seen more common in the past 10 years. These are homemade tablets, and you can see the little markings on them and how they're everything from the Mercedes-Benz symbol to a diamond to a 007 symbol. These are actually made in hand presses or machine presses, just on a small scale, not from some actual pharmaceutical company. And without doing our chemical testing, who knows what's in this stuff? And that's actually one of the scary things about these types of tablets is it really, literally could be anything. It could be ecstasy. It could be something as dangerous as fentanyl, depending on in what quantities. And in fact, that lower picture you're seeing there with the M30s, this is what we're seeing across the country in huge, significant numbers. These are tablets that are actually stamped and pressed with the proper markings for a true pharmaceutical tablet, which it should be oxycodone. But in fact, when we do our analysis on them, they don't have oxycodone in them typically, but they've got significant varying quantities of fentanyl mixed with acetaminophen. And the acetaminophen is there to help mask the fentanyl from some of the more common field testing equipment that we've got. So illicit manufacture of substances, we're seeing it become more high-tech, more complex, particularly with pharmaceuticals like this. If we have a pill like this, we're going to follow one path, whereas if we have something like mushrooms, we're going to follow a different path. Here we've got something that's completely organic, that's you can grow in your basement. And especially when you see this sort of purpley color on the sides of the mushroom, you're more like in the very dark bulbous head on it. Now you know you're more than likely dealing with a type of mushroom that creates within it psilocin or psilocybin. This is a hallucinogenic material. And here's where the chemistry really comes into play, is we actually have to go back to some very old school chemistry, which is this jar in the lower right corner. It's called thin layer chromatography. And if you're taking a chemistry class in high school, and certainly if you take one in college, you're going to be doing thin layer chromatography to start off with. It's very simple chemistry, and what you're actually looking at in that beaker is different dots of black ink out of pens of different brands, and then the vertical stripes, one with yellow and blue, one with just blue, one with red, and one with yellow there. The different ink separates out into its individual color-based components in thin layer chromatography, because the solvent, that liquid at the bottom of that beaker, actually progresses up that plate and pulls each of those different colors out at a different rate. So something as simple as that, something as chemically ancient as thin layer chromatography that's been around for 300-400 years in the chemical world, we still use today in the laboratory, because psilocin and psilocybin in mushrooms like this, some of my high power instrumentation, like something we're going to talk about here in a bit, gas chromatography, can't distinguish them. It's amazing because it's got a hot temperature inlet, and that hot temperature inlet strips one of the atoms off of psilocin versus psilocybin that thin layer chromatography doesn't. So I really like this slide in a basic foundational way, because we're looking at a very natural set of chemicals that are illicit, that are controlled, but that I've got to use old simple chemistry for in order to determine what's what within them. And then we have marijuana. So if our substance looks like a plant material, we're going to start off with a microscopic examination, because as I zoom you in these different pictures, we're getting closer and closer into this bud of marijuana here. As we get closer here, and then all the way down to here, marijuana actually has these bear claw looking things. They're called cystolithic hairs. And this is a not totally unique to marijuana component, but it is a visual characteristic that helps us differentiate between marijuana and something like oregano or the vast majority of all plants that are out there. So that cystolithic hair is what we want to see as one indicator. Interesting thing about that, hops, which of course you find in beer, is related to marijuana. And in fact, hops also has cystolithic hairs in it. So we can't just go by this. We have a series of examinations that we run through in order to differentiate and finally identify what these different potential illicit substances are. So that's marijuana. And then we have color change chemistry, or chromophoric chemistry. This is also something you would find and use even in a high school class, and certainly in college chemistry. And this helps us figure out what family a different type of illicit substance may be. So for example, on the left, if you have marijuana, which possesses tetrahydrocannabinol, which is the active compound within marijuana that really gets your brain going, then the color test chemistry that we use is shown there on the left. You put it in, you shake it up with what's called the modified Duquesnoy-Levine test, add some chloroform, and you can get these two different distinct layers, dark purple over light pink. And if you see that, you know you're at least on the right path for this substance being THC bearing. Whereas on the right, we've got a totally different set of compounds or chemicals that when you put cocaine in there, you get a light pink over sort of an aqua teal layer. Again, using chloroform as one of those layers over aqueous. You shake it up and then it separates out, sort of like oil and water when you're cooking, how those things separate out. So again, very simple chemistry. It all gets documented. It all gets recorded in the examination of each one of the samples and leads us down a path. But in the end, most of what we want to see in drug chemistry revolves around this instrument, which if I was able to actually give you a tour of my laboratory and we walk by this, it's about the most boring piece of equipment you could possibly see, but it is the most powerful one we have. It's called a GCMS, or a gas chromatograph mixed with a mass spectrometer. And how this works is that you've got an oven, a very specifically controlled temperature oven with a coil in it, like a garden hose that is just really, really fine inside. And the cool thing about this instrument is I can have a mixture of heroin, methamphetamine, cocaine, fentanyl, you name it, you put it in one solution and I can inject it into this machine. And that garden hose inside the oven will actually separate them out so that they come out the other end of the garden hose one at a time. And typically a smaller compound, something like methamphetamine, which is pretty small as compared to tetrahydrocannabinol, they come out at different rates. And we call this the elution time. So in the top part of this picture, you'll notice that the X scale or the X axis is 2, 3, 4, 5, 6. Those are minutes. And this is counting off from the time that I injected the sample into the instrument. And you'll see right about 9 minutes, there's this huge spike that goes all the way up to the top of the image. That's THC coming out on this column. And that time, that elution time, is very specific given the temperature settings for particular compounds. So if I had methamphetamine in there, it would have come out of this column probably right about 2.5 minutes. And then I could have zoomed in on that time zone, that peak, and looked at what's called the mass spectra. And that's what's in the bottom part of this screen here is the mass spectra for THC. You can see right there, it says scan 1370, 8.941 minutes THC standard. So in other words, this means this is a known standard that's pure that I injected in the instrument. But all this sort of grass looking stuff with all the numbers on top of it in the bottom pane here. So the tallest one is about 231, 299, 314. And Ling, can you give me a thumbs up? Can you see my cursor moving on the screen or no? Okay, good. So those big peaks there, the 231, the 299, and 314, these actually correspond to the largest fragments of that THC molecule. So as the molecules come out the garden hose at the end, they're being bombarded by an electron gun. And that electron gun just blasts these molecules into bits. But because we're doing it at a specific temperature with a specific electron voltage, that breakup, that fragmentation is consistent over and over and over. So always when I put THC in, whether it's a known specimen or an unknown, I get this pattern with the 314, 299, and 231. It is, if you will, a fingerprint of that molecule. So as long as I have a standard, again, a known, right? Everything in forensics goes back to a known. As long as I've got the known spectra, whether it's the retention time at the top or the mass spectrum at the bottom, and I compare it to the unknowns, this is how we identify something as either THC or cocaine or heroin or marijuana or whatever else. And it's really that simple when you break it down. It's not hard, and everything in controlled substances uses equipment that you may even have at a good high school or certainly at college if you're taking chemistry courses. Pretty simple stuff. And then we're on to blood and breath alcohol. Again, I'm going to try and skim the waves as little as I can for you guys so we can get to a sort of a question and answer there. But blood and breath alcohol, of course, are very important because we have a massive problem, not only in the state, but around the country and certainly even the world, where people are abusing alcohol and then they're taken into custody, particularly when they're driving and doing other things too, but we particularly see it with driving. And we have two main ways of working through this from a forensic standpoint. Alcohol, of course, affects your central nervous system. It's a depressant. It affects your decision-making process, but we have laws instituted that quantify how much alcohol you're allowed to have in your system. And we measure this in two ways, either in your blood or in your breath, because your breath is actually simply a reflection of how much alcohol is in your lungs. And so this slide gives you an idea of how that's measured in what quantities, but honestly, that's pretty boring. The main idea is there's a quantity you're allowed to have and a quantity you're not allowed to have. And the instrumentation we've used throughout the years is varied greatly. This is what the original breathalyzers looked like back in the 50s. And it was simply sulfuric acid that you breathe through, and the alcohol would change the darkness of one vial versus another. So you got one vial here on the left, one vial here on the right. One stayed clear and didn't have your breath bubbled through it. The other one did have your breath bubbled through it. And how dark it got was related to how much alcohol was in your bloodstream and your breath. These days, this is what you'd look like if you're silly enough to abuse alcohol and then go out and drive and get pulled over. This is what you're going to see in some of the substations that you would be breathing into. And it's a very simple system that, again, quantifies how much alcohol is in your breath. So that's a preliminary test. They're still very accurate. But if we really want to measure this alcohol concentration to a greater degree, or if the person is dead, or they're in a crash, or they're incapable, or they refuse to blow into an intoxilizer or a breath machine, then we just suck their blood out. We take that back to the laboratory, we put it into a little vial, and we actually measure how much alcohol comes up in the vapor, the gas, above the alcohol when we heat up the blood. So when I'm doing alcohol examinations, I actually take the blood, put it in a vial with some more solution, stick it in another gas chromatograph and cook it. And it turns this really disgusting brown color, but it balances it. It equalizes how much alcohol was in the blood versus how much is in the vapor above it. And then I actually sample some of the vapor and measure that. So firearms and tool marks. So in the grand scheme of things, like I said, we tend to specialize in different disciplines within forensic science. My specialty is firearms, so this is near and dear to me. So I tend to spend probably too much time on this, but I find this to be the most interesting. Most forensic disciplines, such as latent fingerprints, firearms, and DNA, all have some sort of database, because the amount of data and the number of cases that an examiner like me has to sift through these days is vast. There's no way I could remember all the marks that I might see when looking at one set of tool marks versus another. And so we have what's called a ballistic information network, if you will. It's also called NIBIN, the National Integrated Ballistic Information Network. And if you look at the right side of the pane here, you'll see two primers from two different cartridge casings, and you'll see the similarities and some of the markings on them. This database allows us to put cartridge casings in from unknown situations. Let's say it's a homicide and the person escaped, versus known samples. Again, knowns versus unknowns. So when we get casings from a scene, this system takes a picture of it, stores it away, and then when guns are taken into custody later, we go through all those and we shoot every single one that comes into evidence, and we take a cartridge casing as a known specimen from those guns, put that in the system, and it mathematically looks at the markings that you're looking at there on your screen and presents to the examiner a number of possibilities that it thinks are similar. A true examiner then looks at these and determines whether or not there is actually a match, whether the casing from the homicide scene actually goes from the gun that was collected later. Once again, you can pretty much take everything you've seen on TV about forensics and throw it out the window. It's not an accurate representation of what we do. So whether it is latents or DNA or fingerprints, these systems, these databases that you commonly see on TV are simply a sorting system that they then offer up to the examiner and the forensic scientist a number of options, and we will take it from there and actually do an analysis to reach a conclusion. So if you see NIBIN, that's what it is. It's a sorting tool. Within the firearm and tool mark unit, we do a wide variety of things that you often see on TV. Things such as firearm and tool mark examinations, where we're determining whether or not a casing or a bullet came from a particular firearm, which is just a tool. We also do gunshot residue and distance determination, where if there are particles on a piece of clothing or a body or a wall, we will look at those residues and make a determination of how far away the muzzle was from that object at the time the shot was fired based on its diameter and its density. We can look at how from auto-loading firearms, cartridge casings eject into a scene and then try and figure out an approximate location for a firearm at the time those shots were fired. We can do serial number restoration. Of course, when people steal things, they want to get rid of that serial number so that if they're caught with it, and if that serial number has been reported, they can't then be charged with possession of stolen property. And then fracture matching, which is just like jigsaw puzzle piecing. So let me skim over each one of these a little bit to show you what we do. So with cartridge casings, for example, we're going to start off looking at what are called class characteristics. So for example, the cartridge casing on the left here is a 9mm Luger caliber cartridge casing. It's got a projectile that's about 9mm in diameter, where the one on the right is a .45 automatic. It's much bigger. These couldn't have come from the same gun. It's like mixing apples and oranges. In addition to that, though, if you look at the firing pin impression, which I'm moving my cursor over on the one on the left, and its shape, it's sort of an oval shape here versus circular or hemispherical over here. Even if things are the same caliber and properties like these are different, I exclude them. These things did not come from the same source tool. So unlike what you might get from TV, where you might think the vast majority of what we do is identification, saying that, yes, this bullet or this casing was fired from this gun. Honestly, the vast majority of what we do is exclusion. Nope, this bullet didn't come from this gun, or this casing didn't come from this gun. But we have to go through this sort of layered process, sort of like a workflow. And we look at these class characteristics first. And only if these class characteristics agree, I'm going to go through that in the interest of time, do we then proceed to use these very powerful microscopes, which you can actually see one I've got here at home right above my finger here, where we're looking at things at a magnification setting of anywhere from 10 to about 80x to look at the very infinitesimally small markings and scratches and impressions to see whether there's enough correspondence between these two things to reach a conclusion that indeed a bullet from a scene or a cartridge casing from a scene came from a suspect gun. So if you look at the picture I've got up for you now, there's a dark line running right down the middle where my arrow is going. And what you're actually looking at is a split field line between two totally separate objects. So the one on the left side of that line would be something from a scene, in most cases, an evidence cartridge casing, an unknown. Where the one on the right side of that line is one that I fired from the gun. I collected it as a known specimen. And by putting them on the microscope and moving them around with I have vernier stage control, so just very fine adjustments with knobs, I can get them to align. And you can see that the striations, the scratch marks in this particular picture here show a wonderful agreement of characteristics. And not to get too far into the weeds, but this is called stria in the backflow in the primer. And the gun, the tool, has made these markings over and over again. So when I see this kind of agreement between your homicide cartridge casing and the one collected from the gun collected from the suspect later on, I reach a conclusion that yes, this casing was fired from this gun. And that obviously is something very important that a judge and a jury and attorneys would want to know both leading up to and during a trial that I go into court and testify on and tell a jury, this is my conclusion based on my observation of the physical evidence. Here you've got what are called ejector marks. Again, split field line. You're seeing two different objects, but look at the wonderful agreement in the microscopic tool marks between the unknown and the known. And then on bullets, this is a very high power magnified image. Again, you got your split field line running right down the middle. And look at these wonderful fine stria, or again, scratch marks on one object versus another. It's these kind of very fine markings, particularly on land impressions from inside of a barrel, that allow us to reach these conclusions. Another example, and again, look at the nice scratch marks, the agreement of striations from one to the other. And then on cartridge casings, we don't just have scratch marks from a bullet being pressed down a barrel. Here we've got other kinds of markings. We've got everything from a firing pin impression, which is right here in the middle, to what's called the aperture edges, so that the hole that the firing pin came out of has lots of irregularities in this case too. And then what's called the breech face, the flat part that the firing pin protrudes from in the gun, leaves a bunch of markings such as these guys right here all around it. And these can extend also onto the head of the cartridge casing. So when we get our lighting right and use these powerful microscopes, we're seeing two objects at once, and we're looking for a correlation of these fine microscopic tool marks. With gunshot residue, if you go beyond about 5, 6, 7 feet from the muzzle, we typically aren't going to see any powder particle patterns beyond that distance. I can't tell you whether it was 10 feet or 1,000 feet just based on gunshot residue, but a lot of our shootings are relatively close. And in another presentation in a different audience, I might be able to show you some dead people and show you how powder particle patterns actually embed into skin, and we can work with those pictures. But we, again, have to have a known. So where our evidence, whether it's a dead person's skin, clothing, a wall, whatever, I actually take the gun and similar ammunition and shoot it multiple times at set distances, create a bank of known distance patterns. Here in this diagram, you're seeing them as lines here vertically. And then I look at those patterns, diameter and density, and compare that to the evidence. Again, it's all known versus unknown. So where at close in ranges, if you follow this panel directly down to this one, that powder particle pattern is very, very small in diameter, very, very dense. When I move further and further away from the muzzle of the gun, that powder particle pattern, of course, gets bigger in diameter and lesser in density. I'm going to keep going. I'm already about a half an hour in, so I'm going to keep going in the interest of time. But once again, chemistry comes into play, especially when I have dark clothing like the shirt I'm wearing today. These residues can be very difficult to see with the naked eye, and so I use chemistry to my advantage to raise them, to make them visible. So on the left, you can see what's called the modified grease test. On the right, we have a test using a reagent called sodium rhodizonate that makes lead appear. But if people are interested in going into forensics, that's why the main degree that I recommend is chemistry. Just a basic Bachelor of Science degree in chemistry will get you in the door, whether it's controlled substances, whether it's firearms and tool marks, even something like latent fingerprints uses a lot of chemistry to process evidence. And that's your main thing. Now, if you want to go into DNA, then I would highly recommend going into something more along the lines of biology, molecular biology, things like that. Ejection patterning, again, going through it briefly, many things affect where the casings go when that automatic loading firearm is discharged. It could be how the gun is pitched up and down. It could be how it's rotated, rolled left and right. It could be the surface we're on, but we try and take as many of these variables into account in order to plot, as you're seeing here in this picture, where the gun is. Here you can see it at the center of the Cartesian coordinates here at 0, 0. That's where the gun is. And you're looking down on the shooting range, if you will, from above. And you can see that in this case, I have changed the pitch of the gun from everything from straight down to 45 degrees to horizontal to 45 degrees up to straight up in order to plot where the cartridge casings went from this particular gun. And then I can take a crime scene diagram, lay this over it if I know something about how the gun was oriented, and get a vague idea of where the gun was at the time the shot was fired. And then serial number restoration. So here's the butt of the revolver of a gun, and you can see how the number has been obliterated. It's been scratched off. We have two main techniques we use, one involving magnets and one involving acids, and we can restore it. This one is done with acid. You can see Delta 599547 has been restored on the butt of this revolver. And in fact, in this case, I did this one on purpose so I can show you what it looked like before I destroyed it. And there it is before I destroyed it. So from this completely ground, unable to see anything, to this in the laboratory, compared to its original look like this. So acids and magnets, that's it. And then fracture match. This one can be a lot of fun. And this is a real case I worked probably about, I don't know, 8-9 years ago, where it was a homicide involving a knife. The individual stabbed the person, and from the body, we recovered this piece of metal from the head. We recovered this piece of metal from the ribs of the decedent. And in the suspect pickup truck, in the back of the pickup truck, was this knife. And you can see, of course, it's covered in blood. So the main question, of course, is, did the fragments of metal from the decedent come from this knife, which was collected from the suspect's pickup truck? And so in this case, I took the tip and placed it under high magnification along this knife. And we've got two really cool things going on here. One, the fracture match along this line right here is what you would expect, having broken many things in your lifetime, I'm sure, like I have. You can see how, your broken glass, when you put it back together, it fits perfectly. 1 in a million or more chance that anything else could possibly break and fit together that well. That's a simple. If you like jigsaw puzzles, this is kind of the type of work that might be for you. So you can see how not only the tip of the knife fits in perfectly with the knife from the pickup truck, but also the really cool thing is here, whether it was use and abuse of this knife prior to the homicide, or whether it's actually occurring as the knife's going into the individual. Look at all the damage, all the striations going from one piece to the next. These are actually scratch marks that go from one to the next in the proper pattern, the proper location, that enhance this identification of the tip of this knife going to the knife body that was recovered in the suspect's truck. And then further down here, you can see again how that chip, which you saw right here in the knife, goes together with this chip that was also recovered from the ribs of the decedent. And again, you can see all the use and abuse scratch marks to the knife as well. So double whammy, wonderful identification. No way this isn't the knife that was used to kill the suspect, or the decedent, excuse me. But that's where you really have to be careful in my line of work, is limiting what you say. We have to be very conscious of how far we go when we're writing reports and testifying, because of course, I have no firsthand knowledge that this is the suspect's knife. It's my piece of the puzzle to talk about how the pieces of metal from the decedent go with this knife. It's a detective or a crime scene specialist's job to talk about where they got that knife, or another investigator's job to figure out how they can tie that knife from the pickup truck to a particular person. So it's all a chain reaction, and each person plays their part throughout the investigation. Latent fingerprints. Once again, they have a database. TV will lead you to believe that if you put in an unknown fingerprint into the system, you're going to get a picture and the location of the person as they are right now. You can throw that out the window. Not how it works. Once again, you have to have a known standard in the system. How do you get known standards in there? Well, people who are teachers, people who go into the military, of course, police officers, firemen, pretty much if you want a job that has any sort of security aspect to it and responsibility to it, you may be fingerprinted. And what's called your 10-print card, your known card, will be submitted to a group of individuals somewhere that will put it into AFIS, the Automated Fingerprint Identification System. Now, if somebody hasn't been in that system yet, let's say you haven't been arrested, for example, because when you get arrested, they take your fingerprints and put them in here. But if you haven't been arrested yet and you go and you steal a car and people get latent fingerprints from that car, we aren't going to know who that is yet. The bad part for the person who committed that crime, though, is that this system works both directions, in that if a teacher gets their fingerprints put into AFIS and then goes and turns to the dark side and becomes a criminal and starts breaking into places, well, their unknown fingerprints from the crime scene will hit to them already being in the system. However, let's reverse that. Let's say you, as a young person, commit a bunch of burglaries or car thefts, and your fingerprints as an unknown are collected at a crime scene and put into the system. Might not hit you at that time. But later on, let's say you go to apply for a job to be a teacher, forensic scientist, military, police officer, whatever. Now your known specimen goes in there and they'll still potentially hit back to your criminal activity from years past. So everything goes into this database as a print and it gets stored there for a long period of time. And anything new that gets put in will be cross-referenced to past information, past prints that are in there. Again, I'm going to launch through this fairly quick. I'd really like to be able to get to question and answer, but if you look at your fingerprints, and this goes for your palms as well, anywhere where you have the biological desire, if you will, that it assists you in evolution to be able to grab and grip and have traction, including your feet, you will have friction ridge. And we have basic patterns on things like your fingers, your palms, your feet. like this. If you look at your arms, your legs, your stomach, whatever, you don't have these kinds of patterns. So friction ridge is what this is called, and it is there to give you traction. But it comes in about 5 different basic patterns, and you can look at your fingers and see these patterns on them. There is no significant rhyme or reason as far as what you have on which fingers. It is actually something that develops in the womb when you're developing before you're born. The fingerprint people classify different points of interest in different ways, such as here you see bifurcations, dots, ridge crossings, trifurcation, double bifurcations, etc. And this helps them categorize fingerprints in even a more specific way beyond the ones I just showed you. So again, it's knowns versus unknowns. I can certainly take 2 unknowns from a crime scene, and the fingerprint people can examine them and tell you whether it's the same finger, but that doesn't give you a person. If you're going to get to the person, you have to have the known specimens from an individual. This is what the screens look like in their database, APHIS, and they can do their comparisons right there and reach a conclusion. Where I use a microscope in firearms, they use a computer with a big screen to look at these different fingerprints. And the ones from the scenes, as you see on the left, are not usually that great. They're difficult to look at, whereas something like this on the right, which is a known specimen, an inked fingerprint, it can be a very difficult job. These people have to have a very specific eye and ability to pattern match in order to accomplish this mission. Keep going here. Anymore, they don't really use what you're seeing there. It's actually a little magnifying glass. It really does come down a lot more these days to using big computer screens and scanned in prints. As far as the processing of fingerprints, just like you would commonly see in TV, this is probably mostly true. Dust, powder, and a brush is actually one of the most common ways we still develop what are called latent fingerprints, ones you can't see, so that they can be collected on tape, put on a card, and sent into the laboratory. Whereas some other objects, it's more efficient and more productive to bring them in the laboratory and process them there. So here this person is looking at a CD and processing fingerprints, trying to develop them with a super glue chamber. Super glue, if you ever worked with that in crafting, you might know that if you leave a fingerprint on something, sometimes that fingerprint will develop and you'll actually see it come up as a white cloudy print. Well, we do the same thing just in low pressure in a vacuum with that super glue. We also have chemical dye stains that we use for paper, and that will really help the fingerprint develop there as if it's a latent. And of course, that comes into play with ransom notes and any sort of documentation found in houses to see who has handled paper products. You can't really dust paper products very well. So there, the CD is actually in a vacuum chamber. There's no air in there anymore, just fumes from super glue. And then chemical dye staining. Once a fingerprint is dye stained with some things like rhodamin B and a few other odds and ends, you can actually apply UV light or very specific wavelengths of visible light, and that enhances the fingerprint. So where it was invisible and a latent, now it becomes visible. Now it's something we can take photographs of or lift it with tape and examine it in more detail. And there you go. You get a nice one. This is off a CD, and you can see all the wonderful ridge detail from a fingerprint right there on a CD. Commonly, people think that fingerprints are left everywhere, and that isn't the case. Unfortunately, if you've ever been the victim of a crime where someone's broken into your home, your car, whatever, I can pretty much tell you that in those scenarios, it's a relatively low percentage, let's say maybe 20, 30% of the time, where a crime scene investigator can actually develop a print to work with. The other thing you have to think of is legally where that print is recovered is critical. The outside of your car, if you had a car break-in, even if we develop a print on the outside of a car, it's not going to go to court. It's not going to be good enough. No district attorney is going to take the outside of a car fingerprint and go to court and try and say that that's the person who robbed it, because the easy defense is, oh, I just happened to touch it when it was in a parking lot. Nothing illegal about that. It's got to be from inside the vehicle for a latent fingerprint to really be something that a district attorney is going to be able to run with in court. And then DNA and biology. Here, the acronym for their database is called CODIS. Now, the interesting thing about breaking up these disciplines within the crime lab into different topics, if you noticed, DNA and latents go to identification of an individual, whereas firearms and tool marks, controlled substances, blood and breath alcohol, there we're looking at identifying objects and tactile things that aren't related to an actual individual. So particularly with CODIS, and because of private concerns, or privacy concerns, we have a lot of restrictions that are placed upon us about what can and cannot be entered into CODIS in particular, not so much latent and APHIS, but with CODIS as a specimen. So to enter an unknown sample into CODIS, there has to be some sort of legitimate reason to think that this is a suspect. You cannot knowingly enter a victim into CODIS. And I'm just touching the top of the waves as far as what the rules are or are not. There are people that are very attuned to this because the legal matters of whether it was illegal to put someone in or not are huge. So CODIS is their database. Just realize that particularly in rape cases or cases that are break-ins where blood is left behind, that's where CODIS really comes into play in trying to find and identify a suspect. Now, if someone is arrested for a felony, they can also then be put in there as a known specimen. But that is a very, again, strict protocol for how that person's DNA gets put into CODIS as that known specimen for cross comparison.
So Mike, there's a question in the chat that goes back to fingerprints that came up.
Okay.
And a young lady asked if you could find a fingerprint if someone's wearing a glove. Somebody else commented that they don't think you can. So I thought I would bring that up.
Great question. Okay. Yeah, thanks for stopping me. I can't see the chat the way I've got it set up right now, so I appreciate it.
Totally cool. That's why I'm here.
If you're wearing big work gloves, no, there's no way your fingerprint's going to get through the work gloves. If you were wearing like surgical gloves and latex gloves that you might use for hobbying or for painting, things like that, it actually has been shown that if you wear them for a long enough time, your print can start to embed into that latex, and it almost works like a carbon copy and can come through. Now that's fairly rare and uncommon, but it can happen. But on the reverse side of that, let's say the individual takes off those gloves and throws them at the scene as they're leaving, something like that, we can actually invert the gloves and get the print off the inside of the glove in many cases. So your question didn't have a simple answer. I've given you about 3 different scenarios. The basic answer is in most cases, no, but there are exceptions to that. Okay, back on to DNA. Of course, it seems these days kindergartners know what DNA stands for. You got deoxyribonucleic acid. It's your code. It's what has biologically made you as you develop. And one common misnomer is people think that in the DNA unit, they look at the entire code of someone's DNA and use that to identify who they are. And that's very far from the truth. In fact, when forensic DNA was beginning to come online, they purposefully went to an area of human DNA that does not really code for anything. It doesn't code for the color of your eyes or your skin or how tall you are or how hairy you are or anything like that. It's a junk DNA area. And what they do in that area is they look for what are called repeating sections of the code. So I'm going to zoom through here real quick. They do have a presumptive testing area. I'll come back to this slide here in a second. This one too. I wanted to get to a profile here. Stand by. Long and the short is when someone's doing a DNA analysis, this is kind of what they're looking at. It's kind of a boring chart in the grand scheme of things, but they're looking at specific points in that huge, infinitely long code of DNA that you've got. And each point is called a locus, and plural is loci. And so as you look at this chart here, at the upper left, you can see there's a 12 and a 15. Those two together are at one locus, and this locus is identified as Delta 8 Sierra 1179. Okay? That's a spot that we can reproducibly go back to in every human being's DNA and look at how many times the alleles repeat. So see the 12 and the 15, that's how many times they repeated at that specific point. Similarly, at the next locus, Delta 21 Sierra 11 here, you can see that there's a 30 and a 32.2. Honestly, I don't know enough to tell you about the 0.2. That doesn't make sense to me, but it's DNA, so who knows? But the idea there is that that's the next spot, and you're seeing a number of repeats, and follow it all the way through this chart. Each one of these gray boxes at the top is a locus. These days, we're basically at 21. Some of the old systems used only 17 loci, but by statistical means, the DNA people look at how many repeats are at each one of these spots and figure out what the likelihood is that anyone else in human existence could have those repeats at those loci. And they come to a conclusion in 1 in bajillion, whatever, that anyone else could possibly have that same set of repeated alleles at those loci. it's not as, in a way, complex as looking at entire strings of DNA and coding that. We would be working on our first case still if we had to do DNA analysis in that manner. We're actually looking at this kind of a profile and comparing it. The hard part with DNA is that it's not always the case that we have one person's DNA in the sample, in the unknown. If it's a known sample, we're collecting a buccal swab from someone's mouth, something like that, then it should look clean and pure like this. But when we've got 2 people, 3 people or more mixed in there, then it really gets complex and they may not be able to work with it, unlike what TV would have you believe. But there's, of course, a process. So I'm backing up a little bit here through those slides. And that process begins in many cases with determining whether there's even DNA there. So, of course, biological fluids, and this is one reason why I don't work in DNA, you have to deal with all sorts of nasty biological fluids. But they are first, in many cases, going to check and see with a presumptive test. In other words, one that isn't totally conclusive, but at least lets you know whether you're dealing with a true biological specimen or biological unknown versus, a soda stain or a rust spot as opposed to a blood spot. So those are presumptive tests we can work through right there. But we also have to find the stains. So we can use alternative light sources. Here, this person's working with an ALS, alternate light source, in order to try and make these stains pop as you examine. So here you're looking at a bed sheet, and you can see how this stain just comes out significantly when you've got an alternate light source on it. From there, once they've identified the stain location, they can sample it, cut it out, and begin to process it with a variety of robots, basically. The key thing to take away from the DNA processing part is we can work with very, very small amounts of unknown sample because we have amplification, this step right here. Amplification, I find this very interesting, is a process by which you take the DNA, the helical shape that we've all seen on TV a million times, and you put it into a thermal cycler in combination with very specific chemicals that were actually found in a Wyoming geyser, as I recall. Biologically, it was actually a biological microbe that we found unzipped our DNA and put it back together, depending on the temperature. So we used that biological property of that amoeba or whatever in combination with our unknown specimen in a thermal cycler, which heats up and cools, in order to take one piece, small in quantity of DNA, unzip it, copy it by throwing in more raw material, like throwing a bunch of Legos in a bag, and then recoupling them and then unzipping them again. So cooling, heating. And so you can take one small zipper of DNA and amplify it significantly until we have enough copies of that DNA, and very good copies, to then analyze it and create the profile that I showed you before on that slide right there. Okay. So that's basically the long and the short of how DNA analysis works. It's not particularly complex in its method. It's just very sensitive to the point where we can even swab steering wheels and doorknobs and things like that now and get enough cell structure to amplify, quantify, and analyze the samples and come to a result. In fact, it's becoming so sensitive that it can be difficult to get a good pure sample anymore. That's something they're dealing with in their science. So long story short, I sped up there a little bit on the end with the DNA, but that should give you an overview of the basic disciplines within the crime laboratory and how each one of us does our job and what types of evidence. So, if it's a biological specimen, I'm not going to be looking at it. If it's a controlled substance, then the firearms people aren't going to be looking at that. So that having been said, we minimize that and see if we have any other chats. Does it look like anybody else has asked a question so far, Lane?
Not yet.
All right, so it's supposed to be an hour long, as I recall. So we're at a good point to ask questions. So if anybody has any questions, I'd love to entertain them now.
Oh, okay. So, I don't know. I just find this very interesting. So like with the dust thing, how would, is there any other ways that you'd be able to do that?
As far as fingerprints?
Yeah.
Yep. You could actually use just plain old dirt as long as it was fine enough to work with a latent or invisible fingerprint. And the reason why this works is, throughout the day, your hands get oily, they get other material on them, so that when you press onto a surface, you're not actually transferring so much biological material from yourself, you're transferring all those oils and dirts that you picked up through the day. So you're more likely to leave a fingerprint at the end of the day than as soon as you get out of the shower. But this is only working because once those oils are deposited on the surface, whether it's a forensically produced fine dust or whether it's a fine dirt that you got out in the puerco or something, you could dust it on there and develop a fingerprint just fine.
So like if I were to kill someone like in the middle of the day and they didn't wash their hands, then it would be fairly easy to like detect the fingerprint because they have all the oils and.
By whatever means, the more buildup of oils and dirt they have on their hand, the more likely they are to deposit a fingerprint. So that's my simple way of answering that question.
So if someone would just wash their hands before, then yeah, okay.
Yeah, this is true. And in fact, that's the funny thing is a lot of criminal activity involves, adrenaline and sweating and things like that. So those situations probably enhance the likelihood of someone doing those kinds of activities, depositing a fingerprint. But yeah, if I crawled right out of the shower and then touched a CD, something that picks up a fingerprint really well, I'd be less likely to deposit a fingerprint. And that's another misnomer about guns in particular, is that we get fingerprints from guns a lot because of the textured surfaces on guns. And because they go in and out of holsters or in bags or in clothing, it's actually not that common that we get good quality fingerprints off of guns.
Okay, we have some questions in the chat too. So can DNA change naturally is the first question.
Okay. If you have a bone marrow transplant, you have gene therapy, things like this, then yeah, it can actually affect what your basic DNA is, and it could be different than how it was at a previous time frame. Other than that, from when you're young to when you're old, there can be certainly changes in your DNA from cell to cell in particular. That's what cancer is, right? But as far as the loci that they look at to do this kind of analysis, no. The DNA the profile that you have when you're a baby would be the same as the profile you would have when you're 90 years old, if you make it that far.
Okay, the next question then is, how long does it take to study to be any of these careers?
Very good question. If you were trying to get into this job, number one, don't expect to make a lot of money. It's not like TV where we're all out driving Humvees and Ferraris and junk like that. It's a government service job, so it's not the greatest paying. It's not the worst either, but it depends on where you go and which laboratory. The jobs can be very difficult to get your foot in the door. So I would recommend, again, for most of the forensic disciplines, a good bachelor's of science degree in a physical science, meaning chemistry, physics, biology, things like that. For DNA, definitely biology. And that's a requirement for them. It is becoming more of a requirement to have those science degrees across the country. There are still places where you don't necessarily have to have that for things like firearms and latents, because we do a lot of pattern matching. But in my personal opinion, within a short period of time, you're going to be behind the power curve. And certainly when you go to testify on the stand, think of yourself as a juror. Do you want to hear from somebody that has a degree in, fine art, appreciation, or chemistry, when that forensic scientist, keyword there, scientist, is testifying about their conclusions? So plan on a bachelor's of science degree at a minimum. You can go for master's. There are a lot of colleges now that are providing master's programs in forensic science, if even bachelor's programs in forensic science. And those are also nice to see on a resume. But that's where I'd say to start with. Now, that's just to get you in the door. Once you come in and become a forensic scientist trainee, most of the forensic disciplines have a training program that for something like controlled substances, 6 months to a year, and then you're working cases. For DNA and firearms and latents, more like about 2 more years of training before you're even allowed to touch evidence and start to actually produce casework.
So there's another question that kind of relates to that one, which is, what's your level of experience at the time you got hired with the police department or working in your unit?
Any background experience you can get in a discipline that you're trying to get into can be helpful. So even if you happen to live in a city, you're going to college, you're living in some city across the country, try and get in with the local crime lab, see what lab is around, do an internship. Try and get in there so that you've got some preliminary experience, something that shows you're interested and motivated, and you have at least some idea of how a lab works, so that when you go in for that interview, whether it's that laboratory or not, you can tell them, hey, look, I even spent my spare time volunteering at the crime lab. As someone who's interviewed a lot of people and hired a lot of people at our laboratory, that goes a long, long way. Read. There are plenty of, don't watch TV. There are plenty of true scientific journals to go and look at and documents online to see how laboratories actually operate. Use those to begin to form an idea of how these laboratories work so that when you get in there, you can impress them with what you already know and your motivation. I can tell you right off the bat, the person who sits there in an interview and is kind of timid and says, well, I think I might want to touch a gun sometime for a firearms job is not going to get the job. Whereas someone who says, yeah, I've done an internship. I volunteered my own time at the laboratory every Friday when I didn't have class for a semester and got to know Bob and Dennis and that kind of thing. And I actually was able to test fire some guns. That's going to make the difference in an interview.
So a question that's a little bit more personal is, how many years have you been doing this?
My story is somewhat unique in that I grew up doing this. My dad is probably the best known shooting incident reconstructionist in the world. So when I was in grade school, I'd go out and help him with casework. So for me, I had an unfair advantage compared to many others. If you're familiar with Ruby Ridge, for example, a very famous, infamous shooting event between the FBI and some people up in Idaho, that was my high school. I helped my dad work Ruby Ridge because he was hired to independently do that. So when I came in the door here in Albuquerque, I've been doing this with this police department almost 24 years. It doesn't seem like it could possibly be that long, but that's how long I've been doing it this town. But by the same token, I also operate my own private business. So I specialize actually in shooting incident reconstruction, written a book on it, published lots of papers on it. That's my true love in the grand scheme of things, is how firearms fit into shooting incidents. And that's what I've also been doing for the last 20 plus years of my life, is studying, doing casework, and writing on that.
So another question that kind of you touched on a little bit in the interview process is, are there any mental or emotional skills that you need for this career, like to stay calm?
Yeah, calm is definitely a good one, but I'll tell you right off the bat, sense of humor. You see some of the darkest, most evil things human beings can do to each other. And if you're somebody who gets worried by that, upset by that, you can't stand some blood and guts, or you can't laugh off, a good joke, or you can't laugh off, seeing dismembered bodies and bullet holes and brains spilling out on the ground, go do something else. This isn't a job for the weak-hearted. It's not the job for people who are going to have their feelings hurt. You should go do something else.
Somebody asked if that is an AR above your head.
Yeah, that's actually what's called a short-barreled rifle. It's a papered, short-barreled AR, but yeah, it's a platform, one of the different platforms. Yep.
Okay, let me go.
Well, there are a couple questions it's left in the chat that I want to get to those, but it's coming up in 4:30. So I just want to make the announcement that the attendance survey link is in the chat box. Please make sure to do that. We will stay on for the next couple minutes to go ahead and answer these last questions. So if you want to hear, please feel free to stay on. But if time allows, the session officially cuts off now at 4:30. So thank you for coming, but make sure you do your link before you leave. But yes, if you're interested, please stay on. I think there's some good questions left in the chat, but we need to go. We will see you soon. Thanks.
Okay. So then there is a question. This is an interesting question. What if there are two DNAs mixed? How would you figure out which is which?
Yeah, good point. So you saw at one locus, there were two peaks, for example. Sometimes you can have a major contributor and a minor contributor. So if you have, let's say, two big peaks and you got two little peaks below that, no matter how they're mixed, a lot of times that's how the DNA people will get a good idea anyway, that the two small peaks go to one person and the two big peaks go to another. And they'll work their way through each one of those loci and try and pick that apart. However, if the quantity of DNA from the two donors is about the same, and you just have, for example, 4 big peaks at one locus, you may not be able to. Now, if you know, for example, let's say it's an unfortunate case like a rape, where the unknown sample is a mixture of 2 people, but one, the victim, you can then subtract out the victims by having their known profile, so that all you're left, if you got these 4 peaks and these 2 are the victim, I can separate those out. Now I've just got the other 2 peaks. So there are some logical ways to work through that, but unless you know some background information about the sample source, you may be SOL.
So as a volunteer for an internship, going back to like when you had discussed the internship possibilities, somebody had asked, how do you go about like that process? Who do you talk to get an internship or a point of contact? How do you get your foot in the door?
Yep, great question. Be persistent. Number one, you got to understand that these are government laboratories with people that are really overworked. So if you call a laboratory, no matter where you are in the country, and you leave a message, you don't get a call back, call them back and don't give up. Try and get to a laboratory director. Or if you happen to know somebody personally in a particular unit you're interested in, let's say you want to go into controlled substances, call up the main line at that particular crime lab and say, hey, can I talk to the supervisor of the controlled substances unit? Drop them a voicemail, shoot them an email if you can get their email, talk to them on the phone and say, hey, I really want to do this job. Can you tell me how your specific laboratory operates and what kind of options they have? There are laboratories out there that don't do any sort of internships. Of course, during COVID years, nobody's going to be taking internships, so that's a problem. But when things start to get back to normal, I think they will, then hopefully you'll find just the right person and you'll make that contact. Because laboratories are so different across the way, I can't tell you one specific way to do it, but just be persistent, be annoying to whoever's not potentially calling you back. Keep going. And give me a call if you don't find somebody. I'll try and help you find somebody.
What's the most interesting case?
I'm not giving you my phone number. I'll give you my email though.
What's one of the most interesting? What's one of the most interesting cases you've worked on, if you're allowed to talk about it?
With my private business, I tend to get to travel and see some neat cases more than just the local Albuquerque stuff. And two of them come to mind for different reasons. One, back in 2004, there was an assassination attempt of the president of Taiwan. And you should, if you don't know the history, the political history of Taiwan, you should go check it out. But needless to say, it is complex. And there was a motorcade, and the president and vice president were both shot. The president took a bullet across the stomach, and the vice president took a hit to the knee. But because of their political system, nobody trusted each other. And so they were looking for an outside group of people, forensic scientists, to come over. So I was part of a team. I was the gun guy, but I was part of a team that assembled, and within 2 days of the shooting was off to Taiwan to not only meet the president and the vice president and examine the car and the physical evidence, but to try and put together a picture of what did or didn't happen, because there were accusations both sides. So that was one where going into a political pepper box or tinderbox was interesting, because they were having protests both ways. There was a protest in the main square of 500,000 people the day before I got there. And you got to realize that in forensics, you're not in the happiness business. No matter what you find, it's going to piss one side off or the other. And so you really have to get yourself in that neutral zone of, I'm just going to go with what the physical evidence tells me, shut all the rest of it out, and go from there. But the gunshot wound to the president was right across his stomach. So within a couple of days, he had to drop his pants in front of me to show me his gunshot wound. So really weird stuff like that goes on. And then in addition to that, and that's just part of the story, let me tell you. And then in addition to that, I told you my dad works in this business. I definitely revere the man. He's phenomenal. He's so knowledgeable. I was lucky enough when 2013 rolled around to be a part of a program that PBS's NOVA put together to re-examine the assassination of President Kennedy. And so we went back to Dealey Plaza. I used a tool called 3D laser scanner to rebuild the scene itself and kind of put together some theories about what did or didn't happen. Long story short, yes, Lee Harvey Oswald shot President Kennedy. There is no grassy knoll shooter. You can throw all that out the window. It's a single shooter that killed President Kennedy, but that's another one of my favorites.
Okay. There are two more questions, and then after that, I think we're probably going to have to cut you guys off just to save on Mr. Haag's time. Has there ever been any time that you've messed up and figured out later and had to change something? Does it happen a lot?
Great question. There's no time where I've reached a conclusion that, yes, this bullet came from this gun, and then later reverse that. No, because we operate very strongly off of something called the null hypothesis. And this keeps things like that from happening in association with a very robust quality assurance program where we have verification of our conclusions by other forensic scientists, but that's a whole other story. My main point is, when we do an examination of physical evidence, we always start in the middle of middle of a conclusion, which is, I don't know. I don't know, or inconclusive is the most scientific answer you can ever come to. And as you work through that physical evidence, only once you see enough of a data set, whether you're doing controlled substances or DNA or firearms, only once you reach a certain amount of observations and data to reach a conclusion, do you stick with that conclusion? Otherwise, we stay in the middle. We all have, as forensic scientists, the option of writing a report that says, I don't know, inconclusive. So we're very aware of that. We are very conscious and afraid of making those incorrect conclusions to the point where we always err on the side of caution. So no, I'm lucky enough not to have a situation where I had to reverse an identification or reverse an exclusion and come back and say it was the opposite. Now, you certainly can have gray areas where the verifier and the examiner, let's say one person says, yes, this is cocaine. And the next person in our quality management system comes along to verify it and says, hey, I don't think there's enough sample there. I don't see enough of those peaks that I showed you in the chromatograms before. And so I'm not going to verify this. Let's stick with inconclusive. You know, you can have those kinds of situations. And within our laboratory, we always stick with the most conservative conclusion.
Okay, and then our last question is, what would you do if there were two fingerprints on top of one another? This is from the same student who asked the fingerprint question about if you had gloves on. So I think somebody is very piqued at the idea of fingerprint analysis. Oh.
Nice. As far as a process to work through that, I would say that I probably don't know enough to give you a solid answer because I'm not a fingerprint guy. But I think it's almost, if you take, for example, you know, this set of fingers and this set of fingers, because we have ridges and lines in that fingerprint, you may be able to, as a fingerprint examiner, see the pattern difference between one to the next and work your way through it. And they may even have digital processes by which they subtract out one set versus another. But quite frankly, with fingerprints, if they're smudgy, if they're overlaid on top of each other in a lot of cases, they're going to call it something called unworkable or unsuitable.
Okay. There are an awful lot of thank yous in the chat, Mike, for your time and your expertise and how interesting this has been. So there are quite a few of them. We have a polite group of students. So just wanted to share that with you, that there's a lot of thank yous for your time. And we at MESA thank you too.
Yes.
My pleasure. I wish we could have done it in person. I wish I could have given you a tour of the laboratory itself, maybe sometime in the future.
Yes.
So thank you all for coming. I think that was a great series. I'm going to go ahead and stop the recording now.